We have Peter Ashwood-Smith with Huawei.
Thank you very much. It's my pleasure today to introduce to you shortest path bridging, or the IEEE designation 802.1aq. As a lot of us have been referring to this as just AQ to kind of keep things relatively simple. So we're giving you a couple of new acronyms. Well, why are we giving you these acronyms? What are they good for? If you're working with a Layer 2 protocol, if you are building a Layer 2 portion of your network, for whatever reason you might be doing that, you really have essentially three choices for dynamic control. You have the spanning tree protocols, you have ring-based protocols, and then you have split lag type mechanisms. Each of these has caveats and problems, and so the IEEE has been looking at ways to address these problems, and the 802.1aq, or shortest path bridging, is attempting to do so. And what I will do is go through this protocol for you in the next 30 minutes. So what are the requirements? You know, what are the sort of challenges that are being addressed here by this protocol? One of the first things that we wanted to do was to increase the scale. Currently, the Layer 2 networks are pretty small. We picked the number 1,000. It's an order of magnitude larger than what's currently possible. We wanted to be able to use arbitrary mesh. We want to be able to use the full topology, every single link. If you bother to put a big network together, you should be able to use all of those links. I want to be able to use every single shortest path in the network. Again, if you put the topology together, we want to be able to use it all. And if there are multiple shortest paths, we should be able to use them all. In terms of the multicast mechanisms, we want efficient replication at transit replication points or at the head end. We want to be able to do the same sorts of replication that currently happens with existing Layer 2 networks. Address learning. One of the problems of these large MAC tables distributed throughout a network, we don't want to have to learn these MAC addresses everywhere. And we want to get the recovery times down into hundreds of milliseconds or even smaller for reasonable sized topologies. We want good scale without loops, and we want to be able to create not only this physical topology, but to create lots of logical Layer 2 topologies within that. And while we're creating those logical Layer 2 topologies within that, we want to maintain all of those wonderful properties of the physical Layer 2 within that logical Layer 2. In particular, the ordering, the symmetry of the routing, the congruency of the unicast and multicast, all while using the shortest paths. And this is very important. The last point, we want to maintain all of the OANM, 802.1, the 1731, all of those protocols that have been developed over the last I don't know how many years. We can't invalidate those. This is a simple little example STP network. I'm sure a lot of people are very familiar with some of these issues. Here's a 36-node network. You can see the green links are the physical links. The root of this tree is off there on the left, node 1. And the spanning tree is drawn there in those pinkish links. We can see immediately a couple of the problems with this. I can't physically use all of the links in this network. Well, that's not ideal. The path from the source to the destination over there on the extreme right goes all the way up that tree and all the way back down again, so that's not ideal. And thirdly, all of the addresses off on the source there, hanging off that source node, have to be known by all of the devices all the way up the tree and back down again. So these are not ideal properties for a lot of applications. So what is this 802.1aq shortest path bridging protocol? It's essentially an IEEE 802.1 protocol which builds on top of all of the existing 802.1 standards. So we're not invalidating anything that already exists. It's essentially a new control plane designed to operate with the Q&Q and MAC and MAC data paths. This is very important because all of the existing ASICs out there that support Q&Q and MAC, many of them can operate 802.1aq unchanged. So it's a very inexpensive option. The Q&Q mode is referred to as V mode, and the MAC and MAC mode is referred to as M mode. Again, as I said, backward compatibility with the 802.1 protocols, in particular the AG 1731, and forward compatible, or sideways, depending on how you define it, with the currently being defined data center bridging suite of protocols. But the primary goal of this application, this protocol, is to produce multiple loop-free shortest paths. Okay? We want to use the existing mesh completely, and we want to be able to use multiple shortest paths. In this case, we can currently support 16 shortest paths, and there's opaque mechanisms to allow us to go even further in the future. Multicast mechanisms, two multicast mechanisms. One is a head-end replication model, similar to a VPLS style, and the other is pure transit replication at the appropriate replication points, all within the same protocol. Now, because the protocol is completely deterministic, because the routes are produced deterministically, offline tools allow you to predict exactly where your traffic's going to go. And the nice thing about this is that you can, through head-end assignment of traffic to the different shortest paths, you can do a form of lightweight traffic engineering. And this is doesn't involve CSPF and signaling and all of that, but nonetheless, it gives you a degree of balance and control over your network previously that wasn't available. The ISIS protocol is the link state protocol used to drive shortest path bridging. And of course, ISIS has already been demonstrated to work considerably larger than 1,000 nodes. And so this is a good choice for this protocol. There's already a huge improvement over the kind of scales that we can do with rings or with the spanning tree protocols. The convergence times, well, good convergence times, excellent convergence times with a minimum of fuss. Certainly sub-second, there are paths to get sub 100 millisecond convergence using various hardware multicast mechanisms, and I've got a slide at the very end here which talks about that very briefly. Some pre-standard deployments. There's a 50 or 60 node pre-standard deployment that's actually reporting 300 millisecond recovery times, and that includes all of the replication points and so forth for hundreds and hundreds of services of layer 2 VPNs within that network. The ISIS protocol, as I said, is chosen to support this 802.1aq, and it can operate either as a completely independent ISIS instance, or you can run the shortest path bridging protocol within an ISIS instance that's also supporting IP. The protocol itself really doesn't mind. It's just additive to ISIS. It also supports the multi-topology extensions for ISIS, so that those extensions to ISIS are transparent to AQ. A nice simplification that we did with shortest path bridging was to advertise membership information. So membership in a layer 2 VPN is advertised within the same protocol that advertises the topology. And so what this gives you is a very simple plug and play mechanism. And membership information allows you to create, if you have 2 members, you get an E-line. If you have 3 members or more, you get an E-LAN. And depending on the properties of membership, you can create tree or other kinds of communities. And these are all just variations on the membership attributes. So we have transmit and receive attributes and head-end or transit replication attributes. If you use the MAC in MAC data path mode, shortest path bridging will restrict the address learning to the edge of the network. That's just the basic behavior of MAC in MAC. And in this case, the forwarding database is computed and populated very much the way a router, a Dijkstra calculation computes the shortest path and populates the forwarding table. The main difference here is that the unicast and multicast are populated at the same time, and we also make these guarantees about symmetry and congruence. So the calculations have some special tie-breaking mechanisms that guarantee that the routes between a source and destination will be the same within a given tie-breaking or a given ECMP behavior. And there's a certain amount of tunability with respect to this ECMP behavior as well. You can tweak and twiddle this to actually move the paths around. So, a picture's worth 1,000 words. This is actually a series of screen captures from one of my network emulation tools the guys in my group put together. Shows sources and destinations around an AQ network, and you can see the 16 ECMP paths. So you can immediately see that it's giving a very good set of paths through this network between the different sources and destinations, and all of the links in this particular network are usable. So where would this protocol be of use? Well, there are a number of places. The first obvious place is if you're using MSTP and you want to replace it. And if you do, then you're going to be able to go to a much larger layer 2. You can do this without resorting to the MSTP regions. You're going to have a very low effort to get good routing, because with MSTP you're going to be creating lots of different trees in order to get the routes to go the way you want. Here those trees are automatically created and the routing is automatically shortest path, so you don't have to go to that effort. Convergence times, like I said, are going to be considerably better, and if you use a MAC and MAC data path, you're going to get the address isolation for free. The data center is another application where shortest path routing is a fairly hot topic, and this is in a number of reasons for this. One of the reasons has to do with the fact that there's a lot of traffic between the different servers. Maybe 50 to 70% of the traffic within a data center may actually be between the servers, and of course if you don't use shortest path routing, you go all the way up a tree and all the way back down. It's very inefficient. One of the other attributes of shortest path bridging, which is particularly useful in a data center, has to do with the flexibility of these layer 2 VPNs that are created. They correspond to a subnet, and basically what it means is that you can extend and shrink and grow and move your subnet points of connectivity pretty much anywhere within this physical network over a fairly broad range of nodes. And that's, so I said, that's very important for the virtualization concepts. Compatibility with the data center bridging protocols and OANM. The address isolation, again, is also something that in the data center is very important. Large numbers of MAC addresses coming from all of these different servers. We don't want the core switches to have to know about those, and some form of encapsulation takes care of that. Obviously, we want fast recovery, and we definitely don't want loops. Just talking a little bit more about some of the virtualization. Applications that use the VMware mechanisms, the VMware OANM or vMotion and some of these other mechanisms depend on layer 2 broadcast mechanisms, layer 2 multicast mechanisms. In particular, one of the key ones is in order to move an IP address from one place to another, they do reverse ARPing within the subnet. So the ability to make that subnet go anywhere you want within the data center or within a larger span within that data center increases the span over which these protocols will just work. In terms of things like Microsoft load balancing, one of the modes is a multicast over layer 2. So again, you need a multicast layer 2 solution in order for that to operate, and making that work on a larger scale is a very useful thing to do. VRRP, of course, the multicast between the two routers. So really what's happening here in the data center is that a shortest path bridging protocol simply allows the layer 2 portion of that data center to grow bigger, and that allows the virtualization to operate over that larger span. In a small metro, shortest path bridging can offer a very lightweight and very inexpensive solution for providing layer 2 VPNs. So the E-line, the ELAN, and the E-tree flavors. And so you can think of this as a sort of a very, very inexpensive form of VPLS. You can do the VPLS-style head-end replication by setting a flag one way at a membership in one of these services, or you can set it for multicast replication, in which case, transit replication, in which case it'll behave just like a point-to-multipoint, except without all of the signaling required. So it's, again, the plug-and-play mechanisms will allow you to do this even within a larger scale, such as a metro. So how does this all work? Well, from the operator's perspective, this is really very simple. You plug the N and I's together. You group and the topology comes up. You don't have to assign addresses or do anything fancy there. You then group the logical ports at the unis that you wish to have bridged together, so whatever tagging or untagging forms those logical ports is orthogonal to the protocol. And you then assign a group number to each of them. This is the ISID, the service identifier, and MAC and MAC. And that's all you have to do. They then are bridged, and the traffic follows the shortest paths, and as I just described. Internally, what happens is a little bit more complicated, obviously. The ISIS protocol will read a box MAC address. So there's a box-based MAC, which comes from the factory, or you can configure it if you want. You don't have to. It'll form the NNI adjacencies using ISIS hello, and nothing special happening different. The ISIS will then advertise those MAC addresses. Again, no configuration required. And then one of the differences here is that ISIS will then look at the assignments of services to ports. It will then advertise that information along with the topology information. So now every node in the network knows the complete topology and what services are going from where to where, and it can then compute the appropriate forwarding table entries such that those services are bridged and isolated, obviously, from non-participating members. So what does the data path look like? The MAC in MAC mode, packet arrives either tagged or untagged at a uni. It's encapsulated with the MAC address, source address of the bridge. It's then encapsulated with the service identifier that identifies the group that it is a member of. And then the VID that is used to route the packet through this network is chosen either automatically or based on some offline or user preference. And then the interesting part happens. We look up the end station address. If we find it, well, we know exactly what egress node that corresponds to, what egress AQ node that corresponds to, so we insert the destination address as the egress MAC address of that end box, and off it goes unicast. The interesting thing happens now, of course, if we don't find it. There are two options here if we don't find it. One option is that we can multicast it using a head-end replication mechanism, so we just head-end replicate it to all of the other members of this group. Or if we've selected that we wish to have transit replication, then what happens is that a multicast address is formed that says the packet has come from me, it is going to this group, and the transit nodes have created multicast state that will forward the packet along the appropriate tree to those other members. The unicast transit state or forwarding table essentially produces or it consists of a unique shortest path from this node to all of the other nodes. So we compute those shortest paths similarly to what we would do with Dijkstra and OSPF or IPISIS and install those. The forwarding table, of course, contains a BMAC for each of the other AQ nodes, and it points to the appropriate outgoing interface to get to that along the shortest path that is being used here. We allow this to be repeated for 16 possible shortest paths, and so in a network you might theoretically use 16 BVids total, even if you had 1,000 nodes, to allow you 16 ECMP paths across the network. The symmetry of routing, which is one of the properties here, is assured through special tie-breaking logic, and the 16 different tie-breaking algorithms for equal cost shortest path allow us to produce 16 different somewhat diverse, reasonably diverse routes. Here's a picture, make this a little more concrete. Here we have 6 nodes. I've just shown the last nibble of the MAC address, and between these 6 nodes, between nodes 1 and node 4, there are actually 4 equal cost paths, the pink one, the yellow one, the blue one, and the red one. And I've just shown a little portion of 2 of the forwarding tables here. The leftmost node 1 has 4 entries for the MAC on the right 4, and you can see the different BVids that have been used, 1, 2, 3, and 4, and going to the appropriate outgoing interfaces, in this case 9 and 9 and 10 and 10. And then, of course, the reverse symmetric routes from node 4 back to node 1, again choosing the same BVids that correspond to the reverse route. So if we had services originating at node 1 and terminating at node 4, we would assign them to one of these BVids, and those services would flow along that BVid. Other services could be assigned to other BVids. They would flow on the others, and that would be guaranteed end-to-end. There'd be no divergence from those midstream. So in the multicast forwarding table, it's actually pretty simple. If there's no request for transit replication, there's nothing to do. If no service asks for transit replication, there's no multicast forwarding state in the core of the network. It's boring. It's head-end replication, not worth talking about. What's interesting is the case where the head-end has requested transit replication by the other nodes in the network. And in this case, you get the equivalent of a point-to-multipoint tree, a source-specific tree, but it's done without signaling. It's done specifically by calculation, a deterministic set of calculations. That calculation can be relatively easily described. If I'm a node in the middle of the network and I am on a shortest path between some node A, which is originating some group I, and some node B, which is receiving group I, then I have to produce a portion of that multicast state for this group from that node. So I actually do that. I merge a portion of the multicast state in from node A, group I, to the outgoing interface towards B. Now, in order to do that, I have to be able to manufacture a multicast address. And so this is the actual address format that gets manufactured for the transit replication. In this case, this is a 48-bit, obviously, MAC address. The low order portion of this says what group I'm a member of. So the ISID goes in the low three bytes of this. The high order portion of this is where it contains the source, which node has originated this packet, and we call that the SP source ID. The SP source ID is just a 20-bit identifier, a unique identifier within the scope of this network of where the packets come from. The combination of the source and the group allows us to uniquely identify the tree that this, combined actually with the BVID, allows us to uniquely identify the tree that this packet should be flowing along. And since every node knows what the format is, they can manufacture these very easily. Here's a little example, and there's actually a mistake in this example. Just assume that the link between 3 and 6 doesn't exist because I drew that second arrow incorrectly. But assuming that we have a little 6-node network here, we have the service or the group 255, which originates at node 1 and terminates, or there's a receiver at node 3 and a receiver at node 4. Well, node 5 is on the shortest path between node 4 and node 1, and they share a group 255, so it creates state 2 interface 5. And it's also on the shortest path between 3 and 1, so it creates state 2 interface 6. And the multicast address that it manufactures essentially says it's come from node 1 and it's part of group 255. And if you just kind of by induction do that everywhere within the network, you get the set of trees that are produced automatically in the case where transit replication is being requested. This is another animation. This is a sequence of screenshots augmented with a little bit of extra graphics. What you're looking at here is about a 66-node 802.1aq network, and there is we're highlighting a 7-member ELAN. So there are 7 of these devices that have their uniports configured with ISID 100, and we're looking at the routing that has been produced to bridge these ports together. You can see that I've highlighted each of the trees, starting with that little V shape, that pink-shaped V. That's the root of the tree. And we go through all the different trees in rapid succession. And then for one of them, I highlight the symmetry. So if you look quickly at it, you can see the symmetry between the upper left and the lower right. And that symmetry is true of all of the nodes in the network. The shortest path tree is used in one direction for unicast routing towards the route. It's used in the other direction for multicast away from the route. And it can either be used serially for the unicast away from the route, or the fork points in that tree can be used as replication points if you're choosing to do transit replication. So the control plane. What happens with the control plane? Well, as I said, it's an ISIS link state protocol as the basis for 802.1aq. Nice thing about this is we don't need IP to operate. ISIS can operate strictly layer 2 without IP. That doesn't preclude the use of IPv4 or v6 in parallel with AQ in the same ISIS instance. It's just not mandated or discussed in the standard. The BMAC address is carried in the SysID, but it's also possible to carry additional BMAC addresses for multi-homing. No new PDUs are introduced to ISIS for this protocol. Essentially, 4 TLVs really are all that's required, and a calculation. First TLV is part of the hello mechanism that simply says, hello, I'm running shortest path bridging and I wish to use these vids. We, in the link state updates, have 3 additional TLVs, one of which says, here are the neighbors that I have and the metrics I wish to use for the purpose of shortest path bridging. So I can have additional metrics above and beyond the normal IP metrics in the case where you run the 2 protocols in parallel. We also have the service membership, so the ISID information, which gets advertised. And then there's also some information for the case of multicast, transit replication, what the higher order portion of the MAC address should be if packets are originating from the node which has advertised this. Here's a quick dump of the link state database on a node. I've just drawn a picture on the right-hand side of a topological fragment that you're looking at. We're looking at node 1 that has two neighbors, 4 and 3, costs to each of them of 10, and node 1 sources service 255 and service 256. And so we can see the various components here in the actual link state database. We can see the sysid, which contains the MAC address of node 1. We can see there's a new network layer protocol identifier, the NLPID for shortest path bridging. We can see two new neighbors, neighbor TLVs, cost of 10. We can see some equal cost information about what VIDs are being used within this network. And then finally, and most importantly, we can see the service identifiers, the ISIDs 255, which support transmit and receive, so the various flags you can see down there, and also a 256. So in any sort of distributed dynamic routing system, the issue of looping, loop suppression, and avoidance comes up. It's an important issue. 802.1aq supports two mechanisms. One is a suppression mechanism, one is an avoidance mechanism. Suppression mechanism is essentially a reverse path forwarding check. Because the routing is fully symmetric, both the unicast and the multicast, we can take the SA, look it up in the layer 2 forwarding table, and if we do not find exactly what we expect, which is that it should have come from the interface that it would have gone to if we were forwarding to it, we can throw that packet away. Most of the ASICs that I've looked at actually support this option already in hardware, so being able to either learn or discard allows us to use the discard mechanism in existing ASICs to do this very powerful loop suppression mechanism. However, if you do take a very specific type of network and you simultaneously add and remove several links, it is possible to trap a set of packets in a loop where the reverse path forwarding allows the packet to go in either direction around that loop. So there is also required an avoidance mechanism for that sort of 1 in a million case. And the avoidance mechanism is based on an agreement protocol. The agreement protocol is sort of best described as I agree with each of my neighbors not to move a particular forwarding entry more than a certain distance. And it turns out that if you bound the distance over which a forwarding entry can be moved, and everybody agrees to bound it within certain ranges, then sort of by induction you can prove that a loop is not possible. So that range of movement allows you actually to operate while the forwarding plane is still up, while the control plane is reconverging and only having to remove a subset of entries. That's a 2-hour topic by itself. In terms of the OANM, as I said, 802.1aq doesn't do any OANM. It inherits it by design. So the network layer, the service layer, the link layer, and the network layer OANM. So the 802.1ag, the 802.3ah, and the 1731 stuff all just work transparently on top of this protocol. If you look at things like the symmetry of routing allows, for example, the 1731 two-way delay and one-way delay, or in particular the one-way delay, to give you an accurate response. Because if you divide a two-way delay by 2, you get a one-way delay only if it's a symmetric route. In terms of recovery, I just very briefly mentioned there's a mechanism in 802.1aq where the use of the multicast mechanisms, which it creates for the uniports, can also be used to interconnect the control planes. So we can interconnect all the control planes with multicast forwarding state. And if we do that, and there is a link state update which we have to advertise quickly, we can place it on the multicast tree and have it advertised to all of the nodes very quickly. And this allows us to avoid all of the link state packet comes up to the CPU, do some processing, forwarding it out a link. It can just be simultaneously sent to all of the other nodes in the network. This has a radical effect on the convergence times. So in conclusion, I have in this deck, which I imagine will be available on the Nanog server reasonably soon, if it's not already, there's a worked example for those of you that don't like pretty pictures and prefer to see forwarding tables, probably something worth looking at. There's also a Wikipedia page. If you go to Wikipedia and look up IEEE 802.1aq, we've been trying to keep that up to date, so it'll give you an overview of what's going on. There's also a plan to do an in-depth tutorial, probably at the next Nanog, if there's sufficient interest. And finally, if folks have questions and would like to see how this protocol works on different network types, I actually have an emulator on my laptop, and I'd be happy to sit in the bar afterwards with a beer and draw networks and argue with people about the various pros and cons. Any questions? Thank you. Yes, at the back.
This presentation on the Nanog server. What am I doing wrong? Most presentations aren't on it.
Well, they usually show up afterwards. Okay. My apologies.
Michael Sinatra, UC Berkeley. I think a lot of us who unfortunately have had to work in big, large-scale data centers with big enterprises are really interested in this happening and really want to see this happen where we have lots of complex spanning tree. My main question is why should I use 802.1aq as opposed to Trill if that ever happens? And is it mainly the 802.1 OA and M suite? Is that the big integration win that I get, or are there other reasons in like 30 seconds?
So yeah, no, that's a very good question, and I'm very much a pragmatist. The way I see things right now is we have Trill, which has adopted a certain class of ECMP behavior, and AQ, which has adopted a certain class of ECMP behavior. And I think what you ultimately should be asking for is a composite of the two. I think that it's very unfortunate that two groups of people can't agree on, unifying the behavior. I come from a vendor, and of course we're interested in providing what our customers want. So I think that the right answer is to take the best of both, and of course that requires compromise on behalf of the two groups of people involved.
Thanks. That's good. I just want to say that's very unique. I've never heard of two groups of people in a standards situation not being able to agree and having two divergent standards. But. Yeah,
it's just remarkable, isn't it? But that's one of the goals we would like to accomplish is to bring the behaviors of these two protocols together. And I believe that there are some vendors that are actually already kind of in the middle ground using an Ethernet control plan, an Ethernet MAC and MAC header. They've added a TTL to the MAC and MAC header, and they're using ISIS to control it. So there's already some hybrid stuff going on. So, but if you believe in that, by all means help us and push that.
Regarding the slides, I think someone's trying to work to get them updated. They haven't been updated since I think like 10:30 this morning. But, yeah.
Okay.
All right.
Thank you.
All right.